Okay, this is the time to start the meeting. I think if anyone want to join, he or she can join during the meeting. Now we can start our today's lectures. Once again, good evening, everyone. Uh, my name is Rajat Boni. I am a PMRF research scholar at IITSM Dhanbad, and I get opportunity in NPTL to take lectures, discuss about the sports ground improvement, which is already taught by Professor Dilip Kumar Vaidya sir in his video series in NPTL. It is the third week, which it is also teaching come discussion session. Here in this session today, I am discussing the total third week lectures in PPT form, which is already given by NPTL team. And after that, I try to solve one design problem uh, in this lecture, and also try to solve or the previous year assignment problem in this lecture. And if time is remain, then I will also discuss the previous week's lectures, week one and week two, in few minutes, and it quick session. So let's start. And also, uh, I wish a very happy Independence Day in upcoming Tuesday in advance. So let's start with. I am sharing my presentation. Please wait few seconds. I'm sharing it. Please wait. I'm arranging it. Okay. Uh, Also, I want to tell that my network issue. I have some network issue and technical problem. If anyone having that problem that I am not audible or not visible, please text me, or you can stop me during my or message me during my lectures that the video is not clear or the audio is not clear. And now I am starting with the module 3 and lecture 1, which is this material also shared and by NPTEL team, and the meeting video also recorded. If you don't worry, it will be uploaded in YouTube and also shared by the NPTEL team. And don't worry, if anything miss, if you can see it or go through it by YouTube. And start with our lectures now. In module 3, we discuss about the deep dynamic compression. Uh, in module 1 and module 2, we discuss about the introduction of the ground improvement technique. What are the different techniques we use in ground improvement? What are the different material we can potential material that have potential problem we can address. And in module 2, we discuss the shallow densification, or also called the compaction. What these many things I will already go through it now. Go through it now. I I discuss, or we discuss the deep dynamic compaction in module 3. Let's start. In actually deep dynamic, in name by its name, it is clear that the deep dynamic compaction uh, is used when we want to densify or want to improve our ground very deep, like 10 to 15 meters. Then in this case, shallow densification is not used, because up to 3 meter, up to zero point 0.5 to 1 meter depth only, we can improve the uh, we can improve our ground. So if further beyond that we use the several other techniques. One of that is deep dynamic compaction. It is actually it is actually done by two, only just two equipment. One is crane and another is temper, and no other equipment is needed. In deep dynamic compaction, actually we basically did that we repeatedly drop a weight freely from a crane from a certain height on the ground surface. And actually, from if we drop a weight from certain height, actually we use the energy. That means potential energy. We use and use that energy. By using that energy, we can improve our ground. That means we particle. By applying this energy, high energy, actually the height is almost to 10 to 40 meters. We freely drop from that, and so the weight also 5 to 10 tons. That means it is quite heavy in energy. So by this heavy energy, applied heavy energy, we can densify our ground up to a quite depth. It is simple, just like a shallow densification, where shallow densification we applied up to certain amount of energy. Beyond that, we cannot use. But in deep dynamic densification, we use heavy energy. Heavy in the sense that we applied 5 to 10 tons in weight up to a height of 10 to 40 meter, and drop it freely on the ground. This converted into energy, potential energy, converted to kinetic energy. Then this is a dispersed in the ground, and by this energy, particle to particle friction is remove, and particle get very closer, and so void get reduced. By that means we actually we densify our soil in deep dynamic compression. It is very simple. Only two equipments are needed. One is crane, another one is temper. Temper in the sense is weight which use in this technique, and crane is used for free drop or drop the weight up to a certain depth. That's why crane is used. Now, in the next slide, we discuss the suitability of this technique, or where it is suitable, or where what condition it is suitable, for what soil it is suitable, and what soil it is not. So it is written here that it is suitable, mainly suitable, very loose and partially saturated field. That means it is suitable for cohesion less soil like that. It is very mainly very effective, and it is also suitable for saturated free drain. Free drain in the sense means if it is saturated, and we can apply the load or temper on that, the water which is the excess porous pressure which is developed, which can easily dissipated. That's why it is should be saturated free drain soil, and also it can use with it can use suitable or in silts with plasticity index less than 8, and sometimes it's also used in clay soil. Well, but in clay soil this technique is not at that much effective. But in case if we the degree of saturation of the clay soil is less, that means in the dry season or summer season, we can use easily this technique in clay soil also. But there is some unsuitable problem also due to this technique also, which is not suitable at all. That means it is not suitable in or not recommended in clay soils, because it has clay soil has high plasticity index and high degree of saturation, and also the clay soil has low permeable, that means impermeable in nature. So the dissipated, it is not easily dissipated the excess pore water pressure. So in clay soil, it this technique is not very much suitable, and also it is require drainage and river watering if there is a degree of saturation is very high, because the same thing, same reason is here. That means if if there is not proper drainage or dewatering, the excess porosity generated excess porosity is not easily dissipated. So there should be the drainage and dewatering is required to reduce the excess porosity pressure. Also, if the water table is high, that means if water table is quite high or quite is close to the ground surface, that means the soil is saturated. There, by this also the effectiveness of this dynamic compression is reduced. So uh, in the next slide, we discuss some adverse situation where the dynamic compression has some problems. We cannot apply this dynamic compression or deep dynamic compression. That means if there is soft clay, that means soft clay in the sense the strength of the soft clay is less than 30 kPa. The undrained shear strength, or we can say undrained cohesion, is less than 30 kPa. This technique is not suitable because it has insufficient to resist the temper. It not resist the temper very well, not very well. So it cannot transfer the energy to the deep too deep. So this technique is not suitable for soft clay. Also, when the groundwater high groundwater level, that means the groundwater level is very close to the our ground surface, then this technique is also not suitable because the excess pore pressure is generated and it is quite take time to dissipate it if there is not proper dewatering or drainage. Also, this technique is not suitable because there it is induce vibration. That means after when we the heavy and weight, that means 4 to 10 ton weight we drop from 10 to 40-meter height. That means it is a quite heavy energy we transfer height to transfer to the ground. That if, due to this heavy energy, the vibration is created. Due to this vibration, if there is some close distance, there is some structure that may be collapse or damage. So this technique is not suitable where there is if there is a structure is in order to close to 30-meter or more. And there is also not suitable clay surface because it is inadequate for heavy cranes. That means clay soils is not withstands the weight of the heavy crane. So it is also not used where there is clay surface. Also not used in clay fields because it may subject it to collapse settlement inundated later. That means if it induce settlement in clay fields. Means not compacted. So if you can use the crane may be compact or settle the ground from the beginning. So it cannot use in clay fields. Also, it cannot use in because it creates the flying debris, which is very create some environmental damage or some human. I think it is, causes of respiration disturb our respiration or some other things that is so some precaution maybe or safety may be required. Also, it cannot use where the void ground like crust uh, is available in the below the ground surface, and so it is also not suitable. Also, it is not suitable where biological degradation is material is present because the compaction may create a anaerobic condition and regenerate or change the seat of biological degradation. So this method is also not used where it is biological degrading material is present. In the next slide, we discuss the application, why it is used, or how it, what is the benefits of it. I think in every ground improvement technique, there is a on uh, common benefits or application that is increase the bearing capacity of the soil. In every year, ground report technique, we increase the bearing capacity. So same in this case also, we increase the bearing capacity, also reducing the settlement and minimizing the collapsible potential and mitigating the liquefier potential in for commercial and residential buildings. So coming into the next slide, we discuss here the advantages. What are the different advantages of this technique? The first one is that it improves the large area of geometry in relatively short time at low cost. At low cost, in the means that it is only require two things. One is a crane and another one is temper. By these two equipment, we can easily improve our ground, and it is also quite uh, quick because uh, because it is only two equipments needed or no expertise also not very required in this technique, so we can cover large area in short time. So it is very simple in technique, and also it is effective for loose and partially saturated soil with less than 15% fine. That means it is mainly suitable for loose and partially saturated. Indirectly, it is told that it is mainly effective for cohesionless soil, and also if it is for dry cohesionless soil. So in this case, it is easily transfers the energy to in deep, and no excess pore water pressure is generated, so there is no problem to dissipate the water. So it is quite a quick it is very quick in loose and partially saturated soil which has less than 15% fines, and it also can use to detect the weak or loose areas during the operation. That means when we apply the temper, if the temper is easily penetrate to the ground, we can easily by seeing that we can easily understand that there is a weak soil in below the this ground surface. So we can easily detect where the strong soil, where the weak soil during this operation. And we can also it can also change the heterogeneous material to a more uniform, denser and stronger material. Heterogeneous in the sense that there is some void spaces in it, so material is heterogeneous in nature. After applying the energy, the materials come closer, and there is a uniform strength is developed and denser state is developed. By that it is means it also the major equipment needed for this method is crane. That means it says I already said that in this technique we use only crane and temper, so which is readily available. So this technique is this technique is very yeah, easy to handle, or everyone easy to it is easy to apply in the ground. So no high no sophisticated equipments are needed. So if there is advantages, there is some disadvantages also in this method. These are uh, it- these are it generally not effective to improve the saturated clay soil. That means if saturated clay soil is available, there is created some already told that there is created some uh, excess pore water pressure, and clay already we know that clay is impermeable in nature, so drainage there is drainage problem. So the excess pore water pressure is uh, uh, not dissipated easily. So there is this is the disadvantage in this technique. It is not applied in the clay soil. Also, it induces the noise, vibration and lateral movement, in which we cause some problems in nearby buildings, substructure and utility. Because in vibration or noise there may be some human problems, or diseases occur, or in due to vibration there may be some, or lateral movement there may be some damage occur nearby utility structures or buildings. So this method is not suitable where the in urban area where the many buildings are present. Also, the mobilization cost may be high because we use in this method very large crane or temper. So to mobilize this large crane or temper required quite huge amount or cost to handle this crane or temper. So this method is not suitable for in cost perspective. If the construction cost is less, required construction cost is less, that this method is not suitable because it exceeding the cost of this construction. So also this required instrument to monitor various aspects. In the sense, it required the instrument required for the saturation to know the degree of saturation the ground surface. Also, the equipment required to measure the strength like SPT, CPT. So this method is not suitable where if many instrument required to monitor the ground whether the ground are achieve our goal or not. The improved ground are achieve our goal or not. So this method is not suitable. Coming to the next slide, it is classified. The deep dynamic compaction is classified in two methods. One is dynamic densification. Another one is deep dynamic consolidation. In the dynamic densification is applied for unsaturated granular soil. That means it is applied for dry cohesionless soil. So the in dry cohesionless soil, what happen if we apply heavy energy or temper in the ground, the particle is displaced in denser state and compressed and expel the air out from the voids and reduce the volume of the vessel and improve the ground. So it is nothing but quite similar to the our shallow densification. But here we apply the heavy energy. It's a similar case, similar technique we use in this case. So same thing it is happens also dynamic consideration. It is nothing but the consolidation, but we apply this consolidation happen when we apply the heavy loads. Due to heavy load, vibration is occurred. Due to this vibration, excess pore pressure also generated. So and by this weight, we apply temper weight. We can also the dissipate the excess pore pressure. So it is nothing but quite similar to the consolidation technique. So it is also called the dynamic consolidation. The dynamic consolidation is happen in four ways. First one is compressibility of saturated soil. One is generation and dissipation of excess pore water pressure. Third one is change of permeability, and fourth one is thixotropic recovery. So we discuss one by one these four dynamic consolidation techniques. First one is compressibility of saturated soil. The compressibility of saturated soil is occur up to 1 to 4% of the volume change is occur up to 1 to 4%. Actually, the saturated fine grained soil is incompressible in nature and cannot have volume change under immediate loading. That is undrained condition because in saturated soil, fine grained soil have less permeable, we have less voids drainage path. So the excess pore water pressure cannot easily dissipated. So but some researchers, that is Minier and Boris, give immediate volume change result or for saturated fine soil, which is in the range of 1 to 4%. That means the immediate volume change in the sense when the temper load is applied, immediately the volume, what volume is changed is in the range is 1 to 4%, like that. So in the next technique or next method in conservation is that generation and distribution of excess pore pressure. In dynamic compression, we already told that in dynamic compression induce the excess pore pressure during the operation, and there is some waiting period. waiting period is required to dissipate the excess pore water pressure. That means in the if it is saturated, the dynamic concentration is applied in saturated clay soil or some saturated soil which have fine in content. So drainage path is quite reduced, and also there is a permeability also reduced. So it is take time to dissipate the water, because the less permeable in nature, soil is less permeable in nature, so quite required some times to uh, reduce the excess pore water pressure. So it is nothing but is a consolidation process. So by this same thing is happen in this techniques also. That means it is induce the settlement and compress the soil. So due to the low permeability of fine-grained soil, prefabricated vertical drains some often also used. Actually, prefabricated vertical drain used to increase the drainage path, or also it accelerate the dissipation of the excess pore water pressure, which is already discussed in previous lectures. Then coming to the next slide, it is the other aspect of the dynamic consideration is the change in permeability. Due to apply high energy, vertical fissure are generated. Fissure is nothing but the vertical cracks are generated when we apply the high energy damping. So due to the vertical fissure or vertical cracks in the impact point, the permeability of the fine-grained soil is increased, also accelerated the dissipation of excess pore water pressure, and also accelerate the consolidation. So by this means that it is advantageous that we increase the permeability of the soil. How it is change the permeability or increase the permeability by vertical fissures. When we apply the heavy damping, vertical fissure is developed. Now coming to the thixotropy in nature. The clay soil, or also called the unsaturated fine soil, have one properties, that is thixotropy. Thixotropy is that means that in the sense it is the undisturbed strength by disturbed strength of the soil. In thixotropy, actually first the soil is undisturbed in nature. We apply load, disturb the soil, and it is lose some amount of strength of this soil. So after if we apply, or if we uh, given some time for that, the strength of the soil is increasing after some times. So this is nothing but thixotropy. That means due to the disturbance, or disturbance causing by the temper, it degrades or reduces its strength. This strength is regains with the time due to the thixotropy recovery. This is also the reason why fine-grained soil should have evaluated at least 30 days time. 30 days time is that means time is required to recover his strength or regain his strength in his previous form. So in clay soil, it is quite happen. So it is happening that thixotrophy property, strength is loosened when the energy apply after if we given some time, the strength is regained. This is nothing but thixotropy. So in the next slide, there is a graph by show that four graphs is shown. Here we by this we can describe our dynamic consolidation. In dynamic consolidation, we actually have what we apply. What we do, it is that in first graph we applied energy. Uh, that means from zero. Here we see, you can see that from zero, the from zero to some amount we can apply energy. Then we take some time, or we can apply some time to constant time. The applied energy is available, or we apply a constant time to this energy. After that energy applied, we increase our energy by more amount, some amount. That means we increase our height of fall, or also increase our weight of temper, and also uh, give some time to this weight to settle down, or to improve the ground. After that, also some energy increase our energy. So by this step wise, we increase our energy in consolidation technique, because soil in consolidation, actually it is happening in clay soil. Actually, time is required. Time is required for dissipation of excess pore water pressure. We cannot apply the whole energy in at once. We step by step apply and dissipate our excess pore water pressure. First, if our excess pore applied energy is like that, 1000. First, in first step we apply is 200 or 300, like that, and then give some time, same by same energy, give some time to dissipate the water, and after that we increase our energy. That next, further we increase our energy next, up to 300 to 600, like that we go to 1000 kilo or ton meter per meter square applied energy, like that. Step by step we achieve our goal. So during this applied energy, volume also changes. That means if when we apply energy, sudden volume is changes, and it is constant in few time, and during that same excess supported pressure is dissipated. And further applying more energy, again immediately increase the increase immediately change the volume up to a certain extent. This extent is nothing but the 1 to 4% immediate settlement. This is nothing but called immediate settlement of the clay soil. So also, it is constant few times, and like that it is increasing, the volume changes, and ground is settled down, and our goal is achieved. Or so during this, also degree of liquefaction also changes. That means when we applied the first energy, the degree of saturation go to the 100%, and that means degree of liquefaction, or go to 100% in the sense means the excess water pressure is generated. So we know that the when we applied energy or weight, the total energy or load is first taken by the soil, sorry, water, because water is incompressible in nature. So total weight is taken, total 100% weight is taken by this water. So due to this load, the excess pore water pressure, due to this the water is taken this load, so the excess pore water pressure is generated. So the degree of liquefaction is 100% during the first applied load. So after some certain period of time, the degree of saturation is reducing to up to zero, because the excess water pressure is dissipated through the pore spaces. So like that, after this happening, then if we increase our pressure or increase our energy, again the degree of liquefaction is go to 100%. After certain time, it is due to dissipation of water, it is again zero. So like this it is happening. Then bearing capacity versus time graph. In bearing capacity, time graph, it is nothing but the thixotropy. We show the thixotropy of the clay soil. That means if we apply energy, the soil is disturbed, and strength of the soil get reduced to zero. And after certain period of time, soil is again regain its strength, and so again we apply again the energy. Soil is also the disturbed, and after going reduced to zero. Like that, again it is increase the strength after few times or certain time. Like this, the clay is thixotropic nature, so it is required some certain amount of time. So we can say that 30 days requires after uh, few drops or after a few points, 30 energy applied, 30 days quite something, 30 days are required to regain its energy. After that again apply the energy, again 30 days are required. So the consolidation dynamic consolidation is a lengthy process, lengthy in the sense it is take more time in comparison to dynamic compression or dynamic compaction test, or we can say dynamic densification test. Because this method is not suitable for uh, clay soil, because clay soil, to regain its energy, clay soil requires some time. So it is most suitable to loose unsaturated soil. So coming to the next slide, we discuss about the dynamic displacement. It is why we discuss here. Actually, if we the soil is too soft in nature, that means the soil is not having that much of bearing capacity to take the temper uh, load. So then the soil is displaced. When we apply the heavy energy, soil is displaced, so there is a void space or subsidence or depression is occur. So due to this, that this depression or subsidence is filled by good materials. That means by applying the heavy energy, we displace the in situ soil, and this depression or subsidence we fill by the good or heavy strength material like stone or coarse aggregate. So this method is called dynamic replacement. That means to soft clay soil with a low permeability densification or consolidation is ineffective during and after tempering. Instead of improving uh, the soil is displaced by the tempering and replaced by the stone and coarse aggregate. So it is nothing but replace the in situ material by the some improved or strengthened material like stone and porcelain. So it is all that was all is discussed here. So in the coming slide, it is here shown that few techniques. Sorry, the procedure are described here. How the dynamic replacement is takes place. We can see the first images that we apply the heavy temper from the crane. The ground is subsident like that. After continue the applying the energy or tempering the ground is furthermore subsidized. So like that, there is a depression is created. This depression is filled by the some good materials like stone or coarse aggregate or strengthened material, and we apply again the temper to compact this material, and we created a column type like stone column type in nature. So like that the dynamic replacement technique is applied or happened. So coming to the module 3 lecture 2 in our week 3 plan, we discuss about the design criteria consideration in deep dynamic densification. What are the design steps or what are the factors we governs our designing or design consideration in deep dynamic densification. So it is stated that before the design of the deep dynamics compaction, a geotechnical investigation is required to evaluate the in situ condition. That means geometry investigation like that it is required to find out the bearing capacity of the in situ soil. Also required to find out the cohesion, internal friction, whether the soil is saturated or not, whether the soil is clay in nature or not, percentage of fine contents like that. All the factors are governing the uh, technique. What are the technique we use? These are the factor mainly governs. So these are nothing but the geometrical type, particle size, fine content, degree of saturation, interval T. Also, we have to find out the relative density of questionnaire geometry. Actually, we in questionnaire geometry, we the concept of relative densification is applied. That means we use the degree of concentration. We that means we have to find out the degree of compaction. That means how much the ground is improved after applying the how much percentage of ground is improved after applying the heavy energy. So so in portionless soil, we have to find out the relative densification. This is nothing but the maximum void ratio minus the in situ ratio by the maximum void ratio by plus minimum void ratio. This formula is used. Also, we have to find out the groundwater level. Groundwater level in the sense means the water level is either is close to the ground or not. That means if it is close to the ground, the saturation degree of saturation is quite high. Due to this degree of saturation, excess water pressure is developed. If the ground is not the good drainage is not provided, the excess water is not easily dissipated. So there is some problem happen. A problem occurred due to the groundwater level. So also we have to find out the possible point. That means we have to find out the cast nature, cast geometry. Cast geometry in this means that if the upper layer is hard and there is in deep there is a void, some void is present. If we apply load, upper layer is collapsed, the ground is subsidized, and immediate there is a big depression is in the huge area is happened. So we have to find out the possible birds also in this area. Also, you have to find out the possible sensitiveness in the soil. That means the sensitive means if the collapsible soil or not there is present in not. If there is collapsible soil is present due to vibration, the soil is gets collapsed. The structure is failed, soil structure is failed, and huge depression is created. So we also to take care about the sensitive soil or whether it is a sensitive soil or not. In the next slide, we discuss some influence factor. What are the different factors we actually governs our deep dynamic compaction. This is nothing but the first one is geometrical type. That is whether it is silty in nature or not, whether it is sandy soil or clay soil or not. We know that in clay soil this is problematic in nature. The deep dynamic compaction is not good. So if we this is also a governing factor in our case. Also, we the influence factor is the depth and improvement area. Depth is means up to how much depth we require to improve. If it is zero point 0.5 meter or 1 meter depth is required to improve, the deep dynamic compression is not required. We only use the shallow densification. If it is beyond that, that means 6 meter or 10 meter, then deep dynamic compression is used because it is quite good for or very good for or up to a 10-meter depth. It is very good for to improve the soil. Also, it is influence the deep dynamic compression also influenced by the area of improvement. Area of improvement nothing but the if we apply like that we apply the temper here. The temper here, the like if we say this is ground and we apply the temper is here. Energy is dispersed like that in triangular shape, so or trapezoidal shape. So effective area is improvement area is up to that much. Or in plane section we can say that there is it is the tempered diameter. So effective area is like that. So it is also influenced how much this deep dynamic function also influenced by this area of improvement, whether the area of improvement, how much area of improvement, like one drop or one tempering like that. Also, it is influenced by the temper geometry of weight. How much weight the temper, if it is a heavy weight, the improvement is quite good or very good in nature, or geometry also, either it is rectangular in shape or not, or circular in nature or not, or square in shape or not. Or also it is depend on height and energy. Height, drop height. Drop height in we know that if drop height is more, the potential energy is more. So more energy is transferred to the ground surface. So it is the height, drop height also is a governing factor in case of deep dynamic compression. Also, it is depend on the pattern and spacing of the drop. Pattern and spacing nothing either it is square in nature or triangular in nature, which is suitable, more suitable for the planes, for area. That means if you square in nature is like that, here, 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 or here, we can tempering or drop the our heavy weight. So like that, a square form, square structure is formed. Triangular instance we apply here, here, here. So in between that, here we apply. So like that, a triangular pattern is formed. So which is suitable for your plane area? It is also required to govern our deep dynamic compression. Also, it is influenced by the depth of cutter. We know in the coming slides we know about the deep depth of cutter in details. Actually, in depth of cutter influence the ease of doing the deep dynamic compression. That means if the depth of cutter is more, that it is not suitable to handle the deep dynamic or free fall of the deep dynamic in the deep dynamic compression. So it is also influence our deep dynamic compression. Also, it is influenced by the number of drop and passes. Number of drop means in one point how much number of drop is required or not. Either it is five or four or not. Up to how if actually by increase the number of drop, we actually increase our depth, improvement depth. So you can say if 6 meter depth, up to 6 meter depth we require number of is 4. For 10 meter it is increase like 5 to 6. So like that, how much number of drop is required in one point, and number of passes mean after completing the one cycle again we apply same procedure and apply. So up to how much passes the complete ground is improved, a complete plane area is improved. It is also covered the deep dynamic compression. Also, the induced settlement. Induced settlement in the next, in initial the ground is like that, and after applying the deep dynamic compression, ground is subsided like that. So it is also influence. Deep dynamic compression also influence the induced settlement. Also influenced by the environmental factor, that is nothing but vibration, noise, and lateral ground movement. What is due to vibration and lateral ground movement, the adjacent structure may be collapse or damage. So environmental factor also, environmental impact also address in this. Deep dynamic also in mind in deep, when applying the deep dynamic compression. Also, we can see that with the presence of soft layer or presence of hard layer, whether it is if there is presence of soft layer, the resistance of the ground is not quite good. So the energy applied energy is not transferred in deep. So in top surface of the ground, the also the energy is registered by the hard layer. Energy is not transferred by below the hard layer, so there is some problem. Also, it is governed the deep dynamic compression at the ground level. We already discussed that it is saturated the ground, and it is or excess porosity develop, and it is not good for excess paralysis develop. These also govern the deep dynamic compression, and also elapsed times and pilot trial. These are the many others the factors which is governed. The next slide we discuss the different types of the according to the deep dynamic compression we actually classified the soil in three types. First one is permeous soil deposits.
Why? Three, three, चार, चार, चार. इनपुट रिकॉर्डिंग दिए थे. Hello, hello everyone. Actually, there is some technical and network issue in my in my computer. I can access it is from my friend laptop, so I can continue here from here the rest of our lecture. We have already done discuss about the what are the different what about what is the deep dynamic compaction, and what are the different factors, what is dynamic replacement and design consideration, and like that. And now we are actually discussing in the different types of soil that are suitable for dynamic compaction. One is pervious soil, and second one is semi-pervious deposit. Third one is semi. Third one is uh, semi-pervious deposit, which is one is greater less than 8 plasticity index is less than 8, and another one is plasticity index greater than 8. So in the next it is shown the one of the percentage final by weight by the particle size distribution. It is nothing but shows the different geometrical use or classified the geometrical in based on the particle size and plasticity index. So now we discuss the depth and area improvement. In depth improvement, in depth improvement, we, we actually use the one empirical formula. One is one is in uh, actually depth of improvement depends on the project requirements for desired performance. For example, a loose and saturated sand layer susceptible to liquefaction should be improved to the depth below which no liquefaction will occur. It is given by one empirical formula that is di is equal to nc root over wt hd, where nc is nothing but some constant which is depend upon the degree of saturation of the ground condition and also depend upon the types of different geometrical, which I already discussed that classified in three types geometrials. And WT is the weight of the temper in ton, and HD is the height of the drop in meter. You actually it is one of the empirical formula. So you need also in mind the unit should be in weight should be in ton and height should be in meter. So you keep in mind that the unit should be same while using unit should be in same while using this formula. So by this technique, deep dynamic densification technique, we densify or improve the soil up to 10 meter and cohesive soil in case of cohesive soil up to 5 meter. The area of improvement should be that beyond the area of loading with a distance equal to the depth of improvement on each side. That means we can if we can use the temper like that, we can tempering at this point the area of improvement, that means what will be the area, it is nothing but the equal to the depth of improvement. That is, if your depth of improvement is like the di like that, so area of improvement like di of this side, di in this side, di in this side, di in this side. So total area of improvement should be 2 di by 2 di. It is given in this code. So in the next slide we discuss about the NC, that is constant which is applied in case of deep dynamic in case of find out the depth of improvement. First one is it is actually depend on types of soil and degree of saturation. In um, so in pervious soil, that is granular soil, when the degree of saturation is high, it is zero point 0.5, and when it is low, it is zero point 0.5 to zero point 0.6. But when the degree of saturation is in lower side, the NC value is increased. That means it is quite similar that we know that if degree of saturation is high, depth of improvement is low, or it is difficult to improve our the deep dynamics technique. So in this case, so it is clearly see that we see that the when the saturation is high, the NC value is less. When the saturation is less, NC value is high. So similarly in semi-pervious deposit, when the plasticity in this less than equal to 8, it is in the range from high, for high degree of saturation, it is range from 0.35 to zero point 0.4, and for low it is zero point 0.4 to zero point 0.5. Yeah, similarly for semi-pervious deposit, clay soil, when plasticity is greater than 8, it is for high degree of saturation, it is not recommended, because for that means clay soil with high degree of saturation. So it is impossible to apply the deep dynamic compression. So for this, the value is not recommended, or the test is not recommended. So, but in case of low degree of saturation, when the plasticity index is less than the water is greater than the water content, Then it is range from 0.35 to zero point 0.4. So coming to the next slide, it is discuss about the tempered geometry and why. Actually, temper is mainly the temper is heavy in nature. It can be formed by steel or some concrete or sand. So the in geometry in size in area wise, it is based on 3 to 6 square meter in area. The temper with smaller base area, that means 3 to 4 square meter, are commonly used for granular soil. Are commonly used for granular soil. So, uh, sorry for that. Commonly used for granular soil, and the when it is used for cohesive soil, the temperature will be increased because in cohesive soil the pressure should be transfer is more. The transfer pressure or energy should be more, so the area of the temper should be more, and also the weight is of the temper should be vary from 5 to 40 kilotons. So in the next slide, we discuss about the height of drop or height of drop. What are the height of drop we need when we apply some certain amount of energy? So to find out this height of drop, there is one empirical formula is given. It is nothing but the applied energy to the power 0.454. Here applied energy is WTHD. WT is weight and HD is height of free fall. So we know that when the weight into distance is multiplied, it is nothing but the concluded that it is nothing but the energy. So it is energy. So energy to the power 0.54, we find out the height of free fall drop, and it can be manipulated or adjusted based on our uh, based on our contractor uh, or based on our ground what depth we need to improve our ground. So here we see the pattern and spacing, how actually it is apply in the differential function is applied in the ground. It is actually in phase wise. It is applied. It is here. It is in two phase. It is applied. First one is apply in phase one or phase 1 2, and second one is phase 2. In phase 1, actually what is happen in phase 1 is the circular in given in circular shape. Phase 1 is actually we apply is here, 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 and in phase 1 2 we apply energies here, here, here. And in phase two, we apply energy in all the point here, 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 like that. So, like in this, it is actually square in shape. So, like that means in shape is pattern shape is square. So, like that, we apply in different point in deep dynamification or tempering is done in a ground. So, in the next slide, it is shown the dispersion of energy, how the energy is dispersed. So we can say when we apply the phase 1 the energy is dispersed like that. So after 1 the 1 2 phase 1 2, the energy start from here to here. So again, more the depth is more depth is improved or more area is improved. After 1 1 and 1 2, the phase 2, the energy or we can say the depth of improvement is quite big. So it is here. The graph is here. So after all of the phases, we apply the ionic pass. Ionic pass is nothing but the shallow compaction or shallow densification. Actually, it is done because of that when we apply the tempering, there is scattering is created. Scattering is in the means ground subsidence is created in specific location where the tempering is applied. So we feel the good some geometrical in this depression and apply the ground, fill the geomaterial and apply the ionic pass in this ground. So we can easily leveling the ground by ionic pass after the applying the deep densification. So in the next module, actually we have to very quick because the time is running out. So in the next module, lecture 3, we discuss about the further the depth of crater. So a crater is formed under each tempered drop and each depth increase with a number of passes. The high energy compaction can induce a crater of 1 to 1.5 meter deep, and crater depth should be height of temper plus zero point 0.3 meter to ensure the safety and ease of compaction operation. So actually, crater is formed when the temper is drop a particular location due to the where there is ground depression is occur, ground subsidence is occur, or and also we check the height of the crater. It is mentioned that for safety or ease of compaction, the height of the temper should be the height of the crater should be equal to the height of the temper plus zero point 0.3. It should not be greater than height of the temper plus zero point 0.3 meter. So here to be here given two empirical formula. One is in simple form, another is quite complex in nature. So, but in second formula is give the quite good result in nature, quite good and accurate result of the depth of the crater. But in the field, we use the first one because it is quite simple in nature to apply, or it is simple in nature, and also when we apply some equipment or apply some technique in ground, there is not possible to maintain the accuracy. There is some disturbance in accuracy. So we can use the first formula, which is quite good and simple in nature. It is nothing but the depth of crater is nothing but equal to the 0.28 into number of drops from that point to the power 0.54 and root over the applied energy. Applied energy in the form is weight of the temper into depth of uh, drop of hammer. So here it is said that dynamic compaction of soil with a high degree of saturation would result in deeper crater depth. That means that if you drop of hammer or number of drops is increased, that means in terms of applied energy increase, depth of crater also increase. So in the next slide, we find out given a formula to find out the number of drops. Here it is the one formula is given the applied energy. How much energy we applied for each point. It is given by the number of drop with that point into the weight of hammer or temper and into the drop of hammer or temper, and also the total is divided by influence area, that is nothing but A. Here it is given two formula, one is S square, that is S is nothing but the spacing between the 2 points, and it is given by A is given by equivalent influence area. It is for square pattern is given by S square, and for triangular pattern it is given by 0.87 S square. So, so by this formula we can find out the applied energy at each drop point location. So in the next slide, we can find out the total applied energy. Actually, total applied energy is nothing but the sum of the high energy passes plus the ionic passes. High energy passes means that we apply the tempering or drop of temper of particular location a number of times, and then complete the number of same points one by one after one after, and we covered the area one, then same procedure is applied in second time. So that means the second pass. So during this, the what how much the total energy is applied, it is one, and then after that to leveling the ground we applied the ionic pass. So actually total energy is nothing but the hello. Hello, someone, some mics is uh, okay. Unit applied. So total energy is the sum of the high energy passes plus the ionic passes. So all the energy, the total energy actually uh, we can define by the another terms that is unit applied energy. It is nothing but the total energy applied energy divided by the depth of crater. So, the unit applied energy is so out हो गया तुम out हो गए नहीं चल रहा the ionic mass is mainly used to compact the loosened soil within the depth of crater, and it is given by the formula this unit applied energy into depth of crater. So in the next slide, we in the stability set that unit applied energy. It is given the different unit applied energy for different geometry. First one is given for the pervious coarse grain soil. Second one is given for semi-pervious fine grain soil, and third one is for landfill. So like that. So give me a few minutes or few times. I sorry.
Yes, sir. Okay, sir.
Cooperate. So again we start. Uh, Here we the table is show for different unit applied energy for different types of soil types. First one is pervious coarse grained soil, where applied energy in between unit applied energy in between 200 to 250, and semi-pervious fine grained soil energy, where applied energy 250 to 350 kilojoule per meter cube. And so you should remember the unit. Mainly, is the this energy is given in terms of kilojoule per meter cube, and uh, kilojoule per meter cube. For landfill, actually the applied energy is required more because the landfill it is incompressible in nature, so more energy is applied to compact the ground. So in this case, the required energy is quite big or quite large in nature. And also in the next slide, it is one mm, trial and error is given to identify the number of drops. How many drops are required for one particular location? So it is given by the Chinese Institute Ground Improvement Technical Code. So it is said it is given in 3 points. It is said that the average vertical displacement induced by the last two drops is not greater than 50 m, and when the high drop energy is used, it should be not greater than 100 mm, and no larger heat occur around the crater. And further, the crater should not be so deep that lifting of the temper become difficult. So it is said the here it is said that the vertical displacement induced by the last two drop should not be greater than 50 mm. We can up to that number of drops we need when the vertical drop for last two drop is not greater than 50 mm for a small energy. For if we apply high energy, that should not be greater than 100 mm, and also should not occur heave, any ground heave. If ground heave is occurring, the that means the soil is not suitable for deep dynamic compaction. So this technique is not applied for that. And also the crater should not be so deep after applying the temper. The crater should not be deep, because if it is so deep, the lifting of the temper is difficult and ease of compaction is so difficult. So in the next step, we discuss the degree of improvement. What are the influence factor to improve to in the deep dynamic compaction? First one is geometrical type. We know that the deep dynamic compaction depends upon the different types of geometric types. It is best suitable for the granular soil, that is portionless soil, and also it is dependent on the fine content. Actually, we know that if the fine content is less than 15%, this method is best suitable. So it is also dependent on the fine contents. Also, it is dependent on the groundwater table. That means if the groundwater table is very close to the ground surface, the method is not suitable, because the excess porotal pressure is developed, and due to the dissipation of excess porotal pressure, this method is not quite suitable. And also depend on the applied energy. If we apply the high energy, the method is the depth of improvement should be very high. So it is also depend on the applied energy, and also it is depend on the drop layout. That means whether it is triangular pattern or not, whether it is square pattern or not. Actually, the drop layout is depend on the plane area of the plane area or plane of the area. That means if the area is square in nature, the square pattern is quite suitable. If area is an irregular shape, triangular pattern is quite suitable to improve the ground. So it is also depend on the technique is also depend on the drop layout. Also time. Time in the sense means that the deep when we apply it is in clay soil, the time required to gain its strength, because thixotropy properties is applied for the clay soil. That means it regain its energy. So for that the time is required. Also the time is required to dissipate the excess pore pressure. So these are the factor which is govern the deep dynamic compaction. And in the next slide, it is two graphs is given. One is given for SPT versus applied energy. Another one is given for CPT versus applied energy. So it is by this graph also we can find out the how much energy is required for how what for different SPT value. It means if we explore our ground and find out that our SPT number is 20. So if for sandy and granular soil. For this line is representing the sandy, granular soil, and also miscellaneous fields. And this line is represented for clay field. For sandy fields, SPT value 20. So that much for from we if we draw a line from there, so that much energy from between point 1.5 to 2 energy is required to improve that ground. Also for CPT test, similar technique is used. We explore the ground and find out the strength of the ground. Then we plot the SPT, CPT value in this plot and draw the line and find out the applied energy, how much applied energy used in this process. In the next slide, it is in numerical value. It is shown that how much energy or how much SPT value is required or CPT value is required after or in the dynamic compaction. That means for different types of soil. That means if the soil is pervious in nature, impervious soil means the soil is gravel or sand and gravel. The SPT value is in between 40 to 50 is 50. SCPT value is the 19 to 29. So like that different value is given for different type of soil. So this value is given after the dynamic compression, after the ground improvement. That means if the soil SPT value is 20, before the SPT value is 20, after ground improvement it is 40. So 40 it is 40 for semi-pervious soil or for pervious soil. Let's say granular soil it is 40. So it is means yeah, the strength is improved from 420 to 40. So this table is shown the different uh, for different strength for different types of soil. So in the next slide, it is for the induced settlement. So induced settlement after the each pass, the dynamic compaction, usually bulldozer or something, after are used to level the ground. That means when we apply the tempering, depression is occur after filling this depression and usually you bulldozer apply bulldozer or shallow compaction or roller. The ground is leveling and measure the ground before the height of the level of the ground and after the height or level of the ground is measured and difference measure the difference. So by this we measure the induced settlement. So that means the ground settlement is measured based on the current ground elevation as compared to the original ground elevation. So, in such unsaturated soil, settlement occurs immediately after the compaction. That means the settlement occurs for granular soil and sandy soil immediately because there is no dissipation of excess pore water pressure. So there is no time to require to the dissipation of excess pore water pressure. So it is quite immediately it is happening. And in saturated clay or saturated soil, the settlement increases gradually with time after initial compression under each compaction. It is happened due to the excess dissipation of excess pore water pressure. The dissipation of excess pore water pressure requires some time. So by that time, by certain amount of, after certain amount of time, the settlement is increasing and this densification is further improving for saturated soil. So here it is given that for natural clay soil, the depth of improvement from is the induced settlement is in between the 1 to 3%, and for clay fill it is in between the 3 to 5% like that for different types of settlement. For it is here that the uncontrolled fill, the depth of induced settlement is in between the 5 to 20%. That means it is because it is in high in nature is because the uncontrolled or field types of soil is high in compressible in nature. So it is required a high. It is required. So the settlement is occur in high in nature. So the percentage also is quite high. So in the next slide, we studied the environmental impact. It is nothing but that it is expected that the applying high energy impact on the ground induce the environmental impact, mostly vibration, noise, and lateral movement. This fact has to be considered in the selection of a suitable ground improvement technique. A loose soil or field typically generated lower peak particle velocity. So it is find out that the environmental impact is find out by the peak particle velocity. The peak particle velocity is measure of the disturbance. Locus indicated that the frequency of the ground vibration induced by the dynamic compression is range from the 6 to 10 Hz. That means environmental impact is governed by the peak particle velocity. We actually find out the peak particle velocity for each side after each improvement. Whether it is in comparison range or not. If it is exceeded, that means the nearby structure may collapse or disturb due to the vibration. So it is find out by this empirical formula, which is given, which is that the 70 into root under WT into HD. WT is the weight of the temper, and HD is the drop of drop of height, and HD is the distance from the drop point. Further, we can find the peak particle velocity, and the whole is to the power is 1.4. So here it is one table is given for that threshold value for peak particle velocity. For commercial industrial, that it is in between 20 to 40 per second, and for residential and sensitive it is 5 to 15 and 3 to 5. That means it is means that if it is exceed peak particle velocity from the residential building and from the drop of hammer, the peak particle velocity is increased the 40. That is, this different dynamic compaction is not suitable for that reason, because it may damage the structure nearby. But if it is in between that range, it is quite suitable, and we can apply and go with this method. Now in module 3 lecture 14, we we discuss this slide is already discussed in nothing not is new. We discuss the procedure of the deep dynamic compaction. So the procedure is that the first one is step by step. We discuss the different type of procedure. Different steps are discussed here in procedure. First one is based on the geometrical profile or potential problem. We select the depth of improvement. That is, first we select the depth of improvement di. How much depth we improve, or to what depth we improve. It is either 6 meter or 10 meter. First we decide based on the basic geotechnical profile. That means the shear strength of the soil, initial shear strength of the soil, initial cohesion, yeah, friction, internal friction of the soil, like that. After finding that, we can find out the NC below based on the degree of saturation. We know that we can see we already see that shown that the one table is given for NC in between for different types of soil versus degree of saturation. That means for different types of soil, that means pervious soil, semi-pervious soil, less than passing less than 8. There is different NC value is given. For saturated soil, the NC value is less. For low, high saturated soil, NC value is less. For low saturated soil, NC value is high. Like the different soil, different types of NC is given. So by degree of saturation, we have to choose the NC value. Then we calculate the energy per blow. That means we based on one empirical formula, that is nothing but the di is equal to point NC into NC into root over WT into HD. By this formula, we can find out the find out the energy per flow for high energy impact. Because first we decide the depth of improvement, then we find out the NC based on the degree of saturation, And by this applying this formula, we can easily find out the applied energy for each drop. Then we estimated the drop height. It is also given one empirical formula for that. It is nothing but HD is equal to WT into HD to the power 0.5. By this formula, we can also apply. We also find out the uh, height of height of drop. Then we find out the one table. We discussing one table for total energy. So we will apply. So we based on the geometrical, we find out the what unit applied energy is required for that soil. It is find out for one table we already shown in lecture 3. That is for landfill. We applied the energy from 600 to 1100. Like the unit applied energy, we can choose an in between them and calculate the total applied energy by equation. One equation is given that unit applied energy is equal to the total applied energy divided by the depth of improvement. So by that formula we can find out the total applied energy. After that we calculated the what are uh, calculated the unit applied energy for the ionic pass. That means we know that total applied energy is equal to the applied energy for heavy ionic pass plus applied energy for ionic pass. So, first we find out the applied energy for ionic pass. Then if we subtract the for applied energy for ionic pass from the applied energy for heavy total applied energy, we can easily find out the applied energy for each heavy energy pass. Then in 8, procedure 8 or step 8, we find out the applied, step 9 we find out already, step 8 already discussed. Find out the applied energy for each ionic pass, and we also decide the how many pass is required. How many pass is required for that heavy energy pass. So we also decide the one number pass or two number pass like that. That means we improve the ground one time or we improve the ground two times like that. We also decide. After deciding that, we divide the applied energy high energy applied energy for high energy pass by number of pass, and we get the applied energy for each heavy energy pass. It is nothing but the total applied energy for heavy energy pass divided by the number of pass. After that, applying one formula, we already discussed that the applied energy for heavy energy pass is equal to the number of drop into the weight of the hammer into drop of height divided by the influence area, equivalent influence area. By this formula, we can easily find out the number of drops for each point. So like that we design our deep dynamic compaction, or we apply the deep dynamic compaction in the field. Also we address or we also safety measures, we also address the depth of crater. We know that the depth of crater should not be greater than equal should not be greater than the depth of height of the temper plus zero point 0.3 meter. So we can also, for safety measure, we can also address these points also. Like that, we can apply this technique in the ground. So here is one table is given by FHWA 1986. By this table we can see that what type of temper is used, and for what temper what polar train is used. That means if the weight is 50 to 70 kilonewton, the corolla should be carry is 360 to 440 kilonewton, and also the cable size 19 to 22 mm. So like that, if we increase the temper weight, also the crane capacity should be increased to carry the temper, and also the increase the cable size also to carry the temper. So in this next slide, we discuss about the procedure in schematic diagram. We discuss the procedure of the this technique. That means first we measure the initial level by leveling instrument, like in serving, which we use in serving. After that, we applying the deep dynamic compaction by tempering the ground, and ground subsidence is occur, and also measure the crater depth. After that, we measure the crater depth by same leveling instrument, and also address that, or also see that it should be for safety. It should be in between less than equal to the height of the temper plus zero point 0.3 meter. We should also address that, and after that, we leveling the ground by good material, or backfilling the ground good material and leveling the ground by some smooth roller like that. And then after every step, after that, we again measure the elevation of the ground, and by this differential or subtraction, by measuring the difference in between the initial elevation and after doing the compaction, we can find out the settlement of the ground. How much ground is settlement after the deep dynamic compaction? So in the next step, it is show the temping work, what we do in the field during the temping work. So first step is given that we prepare the site by removing the large objects. This is nothing but the remove the trees like that. Then we also, after that, we leveling the ground, dewatering, and filling the existing pond and local depression area. So like that, first we prepare the ground. Preparing the sense, we remove the debris, remove the large object like trees, and after that leveling the ground. And then and we also address the nearby structure, whether the the nearby structure is in quite a reasonable distance or not. If it is very near to the deep dynamic compaction point, then we apply, or we should trench should be trenches should be used at least 2 to 3 meter deep and 1 meter wide at the bottom of the strange. That means if the depth of deep dynamic compression point is near the near the any structure or utility lines, we dig out one trenches, which is nothing but 2 to 3 meter deep. Why it is needed? Because if the vibration, we reduce the vibration by that. That means we disconnect the ground from there by digging the trenches. So the vibration energy is not transferred to the structure. So the trenches should be here for if the range should be the distance, if the distance should is very less, and then we in place. And also the we address the each pass. After the pass, the drop point, that means the location of the drop point should be maintained. That means the drop point should be center of that area of the depth of improvement or area of improvement. So it should be addressed. Then the position of equipment and movement of temper is right above the drop point. Then survey the top elevation of the temper on the ground. The lift of the temper to desired height, and then let it drop freely onto the ground. Survey the top elevation while the temper is still in the crater. Alternatively, measure the dimension of the crater after the removing the temper. If the temper is still after the reaching the ground, level the base of the crater after the removing the temper. Like that, we can do tempering in the ground. So, in the next module, we discuss the quality and assurance. So, how we maintain the quality and in the ground, or we control the quality or assure the quality in the ground during the deep dynamic compression. So, it is said that the height of the drop and location of the drop should be verified before the tamping. That means there is a plan area plan we already before applying the deep dynamic compaction, we decide what are the different points. If it either quite square in nature, so the points are find out in square pattern or either in triangular pattern or not. Then also need to monitoring and close visual observation we needed made on the based on the monitoring and observation. For example, if one drop location has a much deeper crater depth than the other location, this is an indication that much weaker geomaterial is exist at that location. We already discussed that if the ground resistance is less, that means the temper is easily sink into the ground. So we easily find out or easily identify whether the geometry exists or whether it is not. Like that, the special measure may be like that it is safe. And in the next point, other field monitoring techniques also that is one of is piezometer is used for find out the saturation, degree of saturation of finite geometry. Inclinometer is used to casing for lateral find out the lateral movement, and accelerometer is used for find out the ground vibration. These are the monitoring equipment to monitor the ground during the deep dynamic compression. Also, during the field exploration, to evaluate the degree and depth of improvement after the completion of tapping. Also, you can find out a degree of improvement or depth of improvement after each of the completion of the work. That means if we apply energy WT into HD, what amount of depth is improvement? It is we can find out after uh, each of the drop. And then for coarse-grained geometry, the field evaluation should be performed at least 1 to 2 weeks after the completion of the tamping. For fine-grained geometry, the evaluation should be performed after 3 to 4 weeks after the completion of the tamping. That means it is said the coarse-grained soil required immediate settlement based on the questionless soil. Due to the questionless soil, there is no created the saturation ground is not saturated, so the drainage is sorry, excess pore water pressure is not created. So immediately the ground is subsidized. So the inspection is already is very quick. That means is 1 in 2 weeks. But in case of cohesive soil, that is fine-grained soil, the inspection is occur at least after 3 to 4 weeks. It is required more time because thixotropy occur. The time is required for dissipation of excess pore water pressure. So time is also required for more in case of fine-grained soil. Field exploration includes sampling of laboratory tests, SPT tests, CPT tests. That means after the applying the deep dynamic compaction, we also find out the strength of the material by the different equipments like SPT, CPT. If it is in reasonable range for depth soil, we approve our technique. Or if it is not, we further go for more number of passes or more number of drops for depth soil. If you by that also it is not good for that soil. That means by that increasing the number of drops or number of parts, the soil is not good for the soil increase is sorry, the SPT number of the soil is not increased, then the technique should be changed. Like the other deep dynamics conversion is used like that. So depth of the test should be below the design depth of the improvement. That means we test the result. That means that we find out the SPT value below the depth of improvement. If we pass the below the depth of improvement, the strength is past our requirement. Then to pass our requirement, then we use our this technique, deep diamond compaction. Uh, 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 so next in the next slide, now coming to the last lecture, that is lecture 15, we discussed now one problem of this module. It is quite big. It is a design problem. It is said that uh, which to solve this problem, which we already discussed here, everything is required here. Every concept, little more concept is required here. So now we try to solve this problem. It is said that a construction site is a landfill area. That means the construction site have landfill area consists of a thin top layer of fine grained soil underlying a thick layer of clay silt, which is varying a thickness between the 5 to 8 meter. The fill is that means our depth of improvement should be 5 to 8 meter. The field has moderate to high degree of saturation, and the standard penetration tests were carried out prior to the ground improvement work. That means SPT below is that means soil exploration is done by SPT, and we find out that the SPT is in between 6 to 18, and average SPT value is 9. After the ground improvement by the deep dynamic compression, the SPT value is occur at least 20 for finding soil. And if the dynamic compression is used, the ground as a ground improvement technique provided preliminary design. That means what are the depth of improvement, what are the energy applied, what are the height of the drop, what are the depth of crater, like that we find out. And also it is one to know that to minimize the generation of excess porotal pressure, multiple passes may be used. No matter how many passes also used, we can find out, and use a temper of 20 torr, and both temper diameter is 1.5 meter. It is given 1.5 meter the temper height and diameter, and also that means the temper in shape, the temper is in circular shape. Also, the site of the site exists a residential area at a distance of 20 meter, and the outside the commercial area, other side the commercial area at a distance of 10 meter. मतलब this means we have to find the peak particle velocity and also address whether the test is suitable for in environmental impact or not. Environmental aspect, this test is suitable or not is also find out. So let's start with the problem. First, we fix our depth of improvement. So it is here it is find out that we improve the ground in between 5 to 8 meter. So we can say we select our depth of improvement 8 meter. And by degree of saturation, that means it is here it is said that it is a very high degree of saturation, and the field also fine grained soil. By that we can find out the NC value. So NC value is here is taken 0.35 based on the high degree of saturation and the landfill. The types of soil is landfill. So by this formula, That means by the depth of improvement and NC, we can easily find out the applied energy. That is nothing but W into HD. This depth of energy is formula is given here is Di is equal to NC into root over WT into HD. By rearranging this formula, we can easily find out the applied energy in terms of ton meter. You should remember remember that the unit should be in ton meter for applied energy. So after multiplying into 10, we can it is converted into kilonewton. So we can easily find out this energy. So here we already told that one table is given for NC value is nothing but the same table. It is given already here to find out this. Our material is landfill. That means we can say that it is semi-pervious in nature at high in degree of saturation. So we can take the NC value is 0.35. Then we can find out the height of drop. We can also find out height of drop by this formula, but here it is find out by dividing the temper weight by dividing temper from the applied energy. We can easily find out the drop height because we know that applied energy is nothing but the potential energy. Potential energy is the force into displacement. The forces here is weight of ton of weight of temper in 20 tons, and applied energy is we find out that 5,522. So we can easily find out the height of drop of hammer, and similar result can we can expect from this formula also. Now we further to find out the total applied energy for this deep dynamic compaction, we use the table. Here it is table. One table is required. For unit applied energy for landfill, the unit applied energy should be 600 to 1100 kilojoule per meter cube. So in between we can apply, we can choose that is by averaging that 850 is we find out. So unit applied energy for the whole test is find out or taken from this table, and total applied energy find out by the multiply directly multiply the unit applied energy into depth of improvement. So it is nothing but we find out that 6,800. After that, we find out the total applied energy for irony pass. For that irony pass, we use the depth of crater. Depth should be equal to the depth of the temper or height of the temper. We can use the height of the temper, same height. We can use the depth of the crater is equal to the same height of the temper. And if we multiply the unit applied energy for iron pass, here it is find out for fine grain soil. That means we use the material, fine grain material to fill the depth cutter. So for fine grain soil, applied energy is in between. We can see that 252. Fine grain soil means semi-pervious soil, fine grain soil. So we can use from 250 to 350. In between 250 to 350. So we can easily we take 300 and multiply the 1.5 meter. We can find out the 450 kilojoule. So after that we subtract this value from the total applied energy. We can find out the total applied energy for heavy energy pass. And now if we take the two passes required to improve the ground, so easily find out the applied energy for each pass by dividing the total applied energy for heavy energy pass divided by the number of passes. So we can easily find out 3175 kilojoule per meter square energy for each pass for high energy for high energy. After that, we find out the number of drops for each point. To find out the number of drops each point, we first have to find out the equivalent influence area. Here we uh, applied the square pattern. It is to have the formula is the equivalent applied energy is equal to the spacing square. S is spacing here. So to find out the spacing, we assume that it is the 2 to 1.5 to 2 times to the temper diameter. So we can say that here we take the 2 times of the temper diameter. It is nothing but the spacing is 3 meter. So by applying this formula, we can easily find out, sorry, the unit, there is no unit here, only this number of drops. So by applying this formula, we can easily find out the number of drops for each point for heavy energy pass. After that, have to safety measures or check is required whether the technique is suitable for each point or not. For that, we have to find out the depth of cutter by this empirical formula. Here we find out that the depth of cutter is 1.71 meter. So we already used the depth of cutter is 1.5 meter, and we know that our depth of cutter is 1.5 meter plus zero point 0.3 meter should be required. So total depth of cutter is 1.8 meter. Up to that much of depth we can cutter depth should be up to that much of depth. So by this formula we find that depth of cutter is 1.71 meter. So it is easily shown that the depth is less than 1.8 meter. So this cutter depth we can this cutter depth you can apply, or it is safe or okay, like that. After that, the test is go for settlement criteria. Should be fulfilled first in the sense of in the respect of settlement criteria. Also, it can be fulfilled. We know that for fine grained soil, so uncontrolled field, the settlements happen for 5 to 20%. So by average, we take average, it is 13%. So ground should be settled up to highest point 1 point up to multiplying the percentage into the depth of improvement. We find out that 1.04 meter. That is, up to 1.04 meter ground should be subsided. Beyond that, this technique is not good or not suitable or not pass. To find out the current settlement, we require the uh, energy area ratio. To find area ratio for each point, which it is find out by the area of the crater, cross sectional area of the crater divided by the influence area, or that is nothing but A. Here it is area cross section area of the diameter, uh, sorry, the cross section diameter of the crater is equal to the we taken the equal to the diameter of the temple. So it is 1.5 meter here. By after that we find out the area ratio, that is pi by 4 d square, or we can say dcd square, that is depth of diameter of crater divided by the influence area, equivalent influence area A, which is equal to the S square, that is spacing square. After that we find out the area ratio. So after finding the area ratio, if we multiply area ratio for two passes, we multiply it into 2, and also if we multiply the depth of crater, which is find out from this empirical formula, we find out that it is 0.68 meter of the settlement. So it is quite less than the 1.04 meter. So this technique is suitable for this site. After that, we have to find out the safety purpose. We have to find out our environmental aspects purpose. We have to find out the peak particle velocity. Here it is said that the building, commercial building, uh, in this formula, sorry, in this formula, two area is resident area is given. One is residential area, one another is commercial area. In residential area, it is a distance from 20 meter, and commercial area is at a distance from 10 meter. So for that two distance, we find out the peak particle velocity. For first case, there's the residential area, the 220 meter, it is find out by applying, after putting all the values, it is find out that peak particle velocity is 87 millimeters per second. And the and for 10 meter it is 227 per meter. If two already these two value is exceeded the given table value, so this test is not good for this reason, because it is exceeded the peak particle value which is already given for commercial value 22 and 40, and residential value 55 to 15 meter per second. So it is exceeded. That means vibration is quite high for this reason. The building may be damaged or collapsed. So for this site, this test is not applied because of this reason. Environmental issue. Here we now conclude our session. It is already 8:18. Today there is some technical problem by this for me, so we can address this. We address this session from my one of my friend laptop. We actually we can I cannot access my computer right now. There is a technical problem, and it is already 8:18. We solved some. We solved previous year. I solved previous year assignment problem. I can share to you in Google Drive. No, not worry here. Due to some technical problem, the session is required quite time. So we now stop here. It is already 8:19, and we can meet. We will meet in the next week, this week 4 discussion session. And for the now we closing the our meeting. And if have any doubt regarding this today lecture, you can uh, you can address me in the next session. And also the recorded video recording video is uploaded in YouTube and also shared by the Nptel team. And the and also the materials which I am discussed here and already shared to you by NPTEL team. Now I end the meeting and wish you again wish you the happy Independence Day in advance, which is in coming Tuesday. And also wish you the very happy weekend. So good night and see you soon. Now I am leaving or ending this session.